Welcome back. This is Rashid. Wow, we have come all the way to clock tree synthesis now in our TL2 routing series. So we covered entire flow of synthesis and I spent good bit of time there. And then we had several videos on placement. And now we are on to clock tree synthesis. Okay, what is clock tree synthesis? Why we need it? Okay, I already covered some of these details in there is a playlist you should search on my channel. There is a playlist on clock distribution where I not only cover block level or partition level clock tree synthesis, but I also give you an idea of the top level, how different partitions are there, how clock is distributed, and then also how clocks actually is generated, where does it come, then PLL, the dividers and all that. Okay, so if you want to give a full top level overview, then you can also watch that. But anyway, I think partition level clock tree synthesis is what I'm going to cover here. What do I mean by partition level? Okay, a top level in big design. Okay, in big design, you cannot have one person do entire physical design of the chip. So what you do is you divide your entire chip into smaller partitions. Okay, you can also have, like, some designs are so big, well, I don't know if I should go there. So they can also have subsystems or sub full chips, which for example have 30-40 partition. There is another design as a module hierarchy which has 30-40 partition. So your top level is actually has 3, 4, 5 sub full chips or subsystems, and then underneath you have those partitions. Or sometimes you can also have this top level, it has 40, 50, 60, 70 partitions, and then you have multiple people on, or one person at least on each partition or more, depending upon the complexity of the partition. Okay, so then you have a top level distribution to each. So here is one partition, let's say it has this XY. What you do is clock comes at the port of it, at the port of the, or the actually terminal of the partition, and what happens before that is taken care by top level. Or this is a small chip that you have, a tiny chip that you are taping out, and it's not hierarchical design. In that case, this chip is your block. Then you're not doing any additional clock distribution and all that. You from the pad, your clock comes here. So let's say this is a pad, and then it will be distributed to different parts of the chip. So I just give you a picture here. Let's say on this design you will have flip-flops all over the chip, right? Except where you kind of create blockages, you have macros and all that. But generally, the flip-flop is spread all over the place. I'm just modeling them with the bunch of them are here, bunch of them are here. Now, why you want to do CTS? Why you want to do a clock tree? And what is clock tree? Why you want to synthesize a clock tree? So one option is I don't do anything fancy, right? And what I do is I simply, not like that. I bring with metal here, and then I connect all of them with this, like this, right? And similarly, this one, okay. Simple, just wiring, right? Just bring a metal here, maybe top metal, and then distribute it. Okay, what's the problem with that? Now, if this area is big enough, you can see the problem. Your clock comes here, something like this. Oops, not that. Your clock is here, it arrives like this. And let's say this is a very long distance over this. So what will be the signal here? Well, depending upon how much R and C of this distribution, right? So if you have, let's say this is that input clock, then this signal will not be able to go there. It will go, oops, what's happening here? something like that, right? If you keep increasing this longer or more resistance and capacitance on it, what would happen? The shape of this thing will keep going down like this, right? Even until eventually it doesn't become any proper clock. And the drawback, you know that, okay, eventually the edge is used to capture launch. But the definition of edge becomes harder and harder. Eventually it will become very hard between 0 and 1. This kind of stay in the same logic. You see, this will be a catastrophic for your synchronous design. A synchronous design, they work on clock. Clock is what synchronized data, is what time data. That is your clock. Based on that, you perform a lot of other action in a certain timely manner that you don't create a catastrophic situation. Instead, you properly manage or propagate data from flops to flops. Okay, so you understood why we don't want this? Okay, so then what do we want? Yes, we want to put some regular buffers there so we don't have this situation. What is buffer or inverter? You can put inverter. Inverters, if you remember, just a PMOS and MOS. But buffer has two inverter. Sometimes. Okay. So buffer, you can use inverter. I mean, inverter has full capability that if the signal becomes weak, this is where our CMOS helps us. CMOS is really good in pulling a logic back to VDD or VSS. And so it is very good to kind of remove that noise, to remove this situation. It's kind of a repeater. It repeats the input signal. It tries to recover that input signal. So what you do is you want to put those inverters a buffer. Okay, I'm just gonna do buffer because what is the problem with inverter? Inverter gonna invert the clock. So if you are using inverter, if you have, let's pick a nice color on this one. If this is inverter, you need to have inverter here too, so that the clock doesn't invert. It inverted and comes back. Right. So that's the problem with inverter. You need to make sure you have even number of them. So I'm gonna use buffer. Which one is bad? All right. So buffer here. So I bring a buffer here. So this point has a decent transition time, and then I can put one here. Transition time here. Or maybe you say, okay, Rashid, we don't need it. They are super close. Why are you doing this? Come on. All right, they're gone. So ignore these guys. Can I go back? All right, this is good because deleting them will be very hard. All right, Rashid, you said these are super close. I mean, we are more worried about the far out. Okay, so let's do that. Let's put another one buffer here. Another buffer here. Maybe buffer here. Maybe one more here, right? Kind of, you want to keep the distance pretty regular, so that they kind of repeat after a certain distance together. So that's great for these two guys. Here, okay, yeah, these two buffers can drive them. Here, this single buffer is enough, right? So in terms of this recovering the shape of the signal, I think this will do the job, assuming these buffers are good enough to recover the shape of this class, right? But they do create a problem. Okay, what if there is a timing path between one of these flip-flops? There's an AND gate, inverter, OR gate, to the D pin, from out to the D. You see the situation, or you see the problem? Here clock will, even though with the same shape of the clock is one thing, arrival time of the clock at the clock pins is another thing. So shape is good, we are fine with that, but in terms of when the signal arrives here, so when the clock, if you have this original clock, one clock, this clock here, this has one buffer, so it will be like this, right? This will be, when it arrives here, it will be like this. I mean, it will arrive a little later because of the delay here, and there's a delay here, there's a delay here, right? And what about this clock here? This will arrive maybe, let's make, see, it has, it, once it starts arriving, everything will start arriving the same. So it will maintain this period. Keep in mind, don't get confused with that. So the very first time it will be late, but after that, it will start coming at with the same period that we had here. So period is not changing. There might be some duty cycle fluctuation, but that's a different topic. So D and D. But the arrival time is delayed. So this is delayed, this is delayed. Okay, do you see the problem with them? Setup, hold problems. Right? The delaying could be a problem for setup because your capture cycle is further pushed out now. Sorry, the other way around. Okay, its setup is good because your capture cycle is delayed. You have more time to for data to arrive here, but hold time is impacted. But you can also have maybe a path from here to here. So now you are launching data on a longer path and capturing a short, and that could be a setup problem. So you see the problem with buffering them just for transition time and shape might create a problem for delays. So what you want is this point here or this point here, this point here, you want them because you don't know. I mean, you don't kind of open the design, you figure out which flops have a valid path between them and which one don't, or only balance those ones. You don't want to do that. And maybe even if you did once, maybe logic changes in the next drop, something new appears, right? So that will be very tedious. So what you want is all the flops which are on this clock, you want to balance them with the same delay. So you want to, here comes the proper clock tree. Okay, and this is called H tree because of the shape of H these routes are making. And when you want to put those buffers is, you want to put them that starting from here, 1, 2, 3, 4, 5, 6, 7, 8. This flop is saying 8. So even this flop should see 8. I don't know if we have 8, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it's balanced. So you are taking the clock to the middle, then creating an edge to go there, but your flops are here, then you're creating an edge. So all the flops in these regions need to be connected to this. All the flops in this region need to be connected to this one, this one. So that's where you can cover the entire design. And then if every clock arrives at the same point, then it will have a match latency. So the delay from here to here is called latency. And any delay difference between this point or any flop from this clock, for example, it arrives here at 1 nanosecond and here at 1.1 nanosecond, then you have a skew of 0.1. Okay, so two important things that you understood. One is latency and other is skew. Alright, so in this video I wanted to give you an idea of H3, why we do H3 and how we do it. I mean, that tool does that for us, but basic core concept of that. Okay, in the next video we will look into skew, what is global skew, what is local skew, and all that. So those are important concepts. Don't forget to watch those. Thank you so much. See you next time. Bye bye.